Last week we did the experiment for determining the resonance energy of benzene by using a thermodynamic method to measure this energy difference between a hypothetical model that has 3 localized double bonds and the true benzene molecule that has delocalized pi orbitals hovering above the 6-membered ring. But we didn't talk about the theory behind it, and we didn't really talk about how the calculations should be done, so the purpose of this video is to cover those things. First of all, this is sort of the core idea behind the whole experiment. What we want is this resonance energy, or an estimate of the resonance energy. That is, the difference between, in energy that you get, a measured difference in energy between the localized bonding picture and the true benzene molecule. And if there existed a molecule, this molecule B star, that really had localized double bonds, then we could just do this experiment in a straightforward way. But even then, we would have to have some way of converting this idealized, localized molecule into the true benzene. And the way we do that from a practical point of view is we burn them both. So we burn the localized benzene B star in oxygen to produce CO2 and water. We burn benzene also to produce an equal amount of CO2 and water. And then we say that path doesn't matter in thermodynamics for a state function like energy. And so whether we go straight across, converting B star into B, or whether we go by this other route where first we burn the B star and then we anti-burn the carbon dioxide and water to form benzene, it doesn't matter. We'll get the same energy both ways. And so that says that the energy change for resonance energy should be equal to the sum of the 2 steps on this alternate pathway. So this step, that would be delta U for the combustion of our B star. And then we want the negative of the delta U for the anti-combustion, or well, the negative of the delta U for actual combustion, and that's the anti-combustion delta U. And so the resonance energy that we want is the difference in the combustion energies for B star and for B. The problem is, of course, that B star doesn't exist, and so what do we do about that? There is no B star molecule for us to burn. We have to make some kind of further approximation in order to get some way of figuring out or burning something that's equivalent to this B star. And the way that that's done is we make the approximation that the total energy change is equal to the sum of localized bond energies. So if we take this molecule, the molecule we actually burn, TTTC, and count up how many bonds of each type it has 9 single CC bonds. It has 3 isolated double bonds, so these 3 guys. And notice that these double bonds really are isolated in this case. There's 2 single bonds, 3 single bonds actually, between each double bond. And therefore, they really are a good approximation to a truly isolated double bond. And then there's 18 CH single bonds for all the hydrogens that aren't shown here around the periphery of the molecule. But that's not quite right? For a single benzene B star, so for a localized benzene, there should be 3 CC single bonds, there should be 3 localized CC double bonds, and there should be 6 CH single bonds. This is clearly something sort of related, but it's got a lot more CC single bonds. It's got the right number of double bonds, but it's got way too many CH bonds as well. So what we do is we also look at cyclohexane here. That's got six single CC bonds and 12 CH bonds, right? 2 CH bonds on each corner here. And so if we subtract the bonds in this guy from the bonds in this guy, then we get the correct number of bonds. And what that says is that at this level of approximation, where you can really just add the bond energies together, and it doesn't matter what molecule they're in. If it's a double bond, it has the same energy in one molecule as it has in any other. If it's a single bond, it has the same energy in TTCC as it does in cyclohexane. That says that if you subtract these two, you'll get the right numbers of each type of bond, and that's the basic approximation behind the two. And so what that says is that our resonance energy, or an estimate of our resonance energy, should then be the energy of combustion for TTCC minus the energy of combustion for the cyclohexane. All of that is our estimate or our approximation for the combustion energy of B star, minus now the combustion energy for benzene, which we can get directly because benzene is a real molecule. So far, so good. That's all reasonably straightforward, and this relationship that I have here outlined in red would be just fine for the calculations for this lab, except that we're only going to burn TTCC. We're not going to burn the other two. We're going to use literature values for these other two quantities, but we don't have delta U values for the literature. We only have delta H values. That's one complication. We need to somehow get delta U values from delta H values in the literature. The other complication is that it's a little bit subtle, but notice that all these are gas molecules. We're looking for the difference in energy between gaseous TTCC, gaseous cyclohexane, and gaseous benzene, but at normal room temperature and pressure, all those guys are in fact liquids. And we don't want to do things from the liquid phase because then that involves extra energies, right? That involves energies of interaction between the molecules. We want to use the gas phase because the gas phase is a good approximation to a molecule that's truly in vacuum and not interacting with anything else. So if we want the resonance energy, we want the vacuum difference in energy, not the liquid difference in energy. All right, so in order to deal with that latter thing, in order to get the delta U for a gas phase molecule, we notice that again by the same kind of thermodynamic logic, we can use the gas phase, the liquid phase combustion value, and then subtract the delta U for the vaporization. The idea is that if I burn some liquid and get CO2 plus water, that's the same thing as if I first vaporize the liquid to the gas phase and then burn it, right? Same, it's a different path, but delta U's don't depend on path. So if I look at the energy by this other path that gives me the same results, CO2 and water, I will get the right answer. So I can burn the liquid stuff and then subtract the heat of vaporization, well, not the heat of vaporization, the energy of vaporization, and I should get the right answer. There's no approximation here. That's actually rigorous. So with that relationship, we have that our resonance energy, our estimate of the resonance energy, is the delta U for TTCC in the gas phase for combustion, but that's the same thing as the delta U in the liquid phase for combustion minus the delta U for vaporization, and the same thing for cyclohexane and the same thing for benzene. So now instead of 3 terms in our relationship, we've got 6. But that's not a big problem, right? 6 terms we can deal with. The next level, the other part of the problem, is that we don't have any of these. So all these numbers, everything except the one number that we're measuring, we have to get from the literature. Let me say something before we go on, though. Do we really have a delta U? When we measure the numbers from the bomb calorimeter, do we get a delta U value? What do we get? Well, the bomb calorimeter measures heat exchange for a constant volume process. For a constant volume process, the heat change is the CV times delta T, which is the same thing as the delta U, the energy change for the system. If it were a constant pressure process, if we did this in a coffee cup calorimeter or something, the heat exchange would be the Cp times delta T, and that's the delta H value. So the reason why we really do get this delta U value is because we're using this constant volume big hunk of steel that keeps the volume constant, even though we're lighting things off in there. So it can resist the pressure. That's why it's steel. And it's also the reason why we're not using the coffee cup calorimeter. We really do need this delta U value. We need a delta energy value, not a delta H value. Why do we need a delta U value? Well, because we're trying to get an energy difference, a resonance energy difference, right? Not a resonance enthalpy difference. The enthalpy delta H is equal to delta U plus P delta V for a constant pressure process. The delta V term there is accounting for the energy, the work that's done when in a constant pressure process, when the system changes volume. And we don't want that. We just want the delta U value. We don't care about any work terms that come from pressure and volume. We want to know what the actual microscopic energy difference is between this localized molecule and the delocalized true benzene molecule. And so we need delta U values in order to do what we're trying to do. And that's why we're using a bomb calorimeter to actually make the one measurement that we're making. That leaves us, though, with all these other values that we need in order to do our calculation. They all have to come from the literature. All the literature values, it turns out, are delta H values, and so somehow we're going to have to get delta U values from literature delta H values. Here are the delta H values that we need. Here's the delta H's of vaporization. Here's the delta H's of combustion. I got these from the write-up. You can get them, I think I wrote them down accurately, so you can get them from here if you want, but they were also all in the write-up, so you can get them from there too. Anyway, the point is that they're all delta H values. There's only one value that we don't know. That's the delta U, or the delta, well, it's not a delta H, it's a delta U of combustion, and that's the one thing we're measuring. In order to convert these delta H values into the delta U values that we need for up here, we're going to assume that all the gases that are produced in the course of the combustion reactions are ideal gases. The delta H value that we have in the literature is delta U plus delta PV, but if the ideal gas law holds, then PV is equal to nRT, and so delta PV is equal to nR delta T. Sorry, the other way around. For a constant temperature process, it's RT times delta N, where delta N is the change in number of gas molecules or gas moles that took place during the course of the chemical reaction. So, for example, if we burn TTCC in the gas phase with the appropriate amount of oxygen, and we get a certain amount of CO2 and a certain amount of water vapor, and assuming that all these things are in the gas phase to start with, then delta N would be, we're gaining 9 plus 12 or 21 moles of gases, And we're losing 33 halves, or what is that? That's 16 and a half moles of O2, of gases. Actually, 17 and a half if TTCC is also a gas. And so delta N for this reaction would be, what, 3.5? Actually, it would be plus 3.5, right? Because there's more moles of gas on the product side than there is on the reactant side. And that's the idea then. If delta H is equal to delta U, let me rewrite it here. If delta H is equal to delta U plus RT delta N, then delta U is equal to delta H minus RT delta N. And therefore, if we have a delta H and we know what the delta N is for a given reaction, we can get the delta U value. So the rest of the details of that are given here. So for burning the cyclohexane, for example, the delta N value ends up being minus 3, which means that there was more moles of gas to start with than there are at the end, assuming that we produce liquid water and not gaseous water. I say I think that that's the case because it's what makes sense with all the rest of the calculations, but that isn't actually spelled out in the write-up. I'm 100% sure, really, well, 98% sure that this is correct, because otherwise the whole calculation wouldn't make sense. But that's a deduction on my part. I don't have an authority to cite for that. Anyway, if that's true, then the delta U of combustion of the liquid is equal to the delta H of the combustion of the liquid plus 3 RT. Yes, and then likewise for burning the benzene, the delta N value is minus 3 halves, and so delta H of combustion of liquid benzene is equal to, delta U for that, is delta H for combusting liquid benzene plus 3 halves RT, and so on. For the heats of vaporization, we're going from a liquid to a gas. Delta N is plus 1, and so that says that the energy of vaporization, or the change in energy of vaporization, is the delta H of vaporization minus RT. And using those relationships, we can convert all these delta H values up here to delta U values and then plug them into the formulas that we have below. That's what I've done down here. I won't go through it in detail. You can do that yourselves. And probably you ought to, in an appendix, you ought to go through this in detail to explain to us and to Amy exactly where these formulas come from. But if you substitute all the relationships together that I've just gone over, this is the final relationship that you get. I think I've talked about everything else, and anyway, we're done with the experiment, so I don't think there's anything else left in this write-up. Let me just point out that everything I used here, everything I pointed out here, is from a set of notes that is up on Learn already, and so you can go over it at your leisure and go over any of the pieces and details that you may have not followed when I was going over it here in this lecture. Thanks.